the biggest challenge itself is the process which we need to be followed, because in automotive industry, even if you want to put a small hole or a small nut, it's a huge process to follow. It's a very big process to follow. Trust me, I had affiliated with
I
OEMs
mean,
in the
it
past.
involves people's life, so
Yeah,
it
exactly.
makes. Welcome everyone to the first video of our new series where we interview the community vote winners of the University Technology Exposure Program. To learn more and participate in the program, you can check out the link in the description. Today, we'll be chatting with Srikanth Kolachalama to learn more about his research project. Srikanth, can you tell us a bit about yourself and the background that got you started working on vehicle optimization and also adaptive cruise control?
Absolutely. Firstly, I would like to thank you, Wevolver, for this opportunity. It is very motivating and very exciting for us. So, precisely speaking, I'm a researcher at University of Michigan. I'm affiliated with Dr. Malik's laboratory. We are pretty much we are an interdisciplinary branch, pretty much focused on multiple areas. One area is automotive cybersecurity. The other one is machine learning and analytics, and one is performance analytics. Like performance is automotive systems engineering. So I started working on this research project, and precisely speaking, the our research is pretty much focused on understanding the driver behavior vector and how does it augment the automotive performance. As an example, one thing would include most of the engineers in the past had developed techniques and technologies and features which are pretty much integrated in the car. How, like example, spark ignition timing, optimizing the crankshaft timing for improving the automotive performance, so and reducing the fuel economy, as an example, fuel economy mode.
Yep.
So in our work, rather than what engineers have done for the car,
Mhm.
we are pretty much focused on what driver is doing to the car to improve the car's
Yep.
performance. So one of the most important element of this is the speeding behavior. Like how well is he speeding? How well is he
Yep.
accelerating? What kind of parameters are being deployed? So that's how this project started as of now, because ACC is one of the best features which provides controlled acceleration and deceleration,
Yep.
and we began the project on that.
Yep, that is that's very interesting. So
Mm.
like adaptive cruise control has become like one of the the technology has trickled down to like common cars. Like this technology is not only for like the most high-end cars. They are now available in the market for at a more affordable price, right?
Mhm.
So what does your technology offer compared to like the conventional ACC that's already like implemented in most cars in the streets right now?
Good. To give a brief history of ACC, the cruise control technology was patented sometime in mid 90s approximately. So it is there in the car since long time, and
Yep.
for the past decade, I think it is deployed in every basic model. Previously, the customer has to pay money for that. Now it is deployed in every
Yep.
basic model almost. So we are not developing a new feature as such, but we are proposing a big change in the complete ACC functionality. As an example, what we did is like the driver actually inputs the set speed value for the ACC feature, which is a prerogative of the driver, and that it's a command given to the car to drive at that speed. But right now, we proposed a complete deviation in the functionality. The driver will no longer input one value; he will input a range of values. As an example, if you're going at 70 on a freeway, you're setting a value. You don't put as 70; you put it as 65 to 75, or speed limit plus 3 or minus 3. Again, the car follows the driver command, but in a certain speed. This is one of the big deviations which was never proposed before, and we had proposed that in our article.
Okay, so basically the difference is like instead of having a one exact number where the car needs to obey that exact same number, you can
Yeah.
like put a range, and then
Yes,
like the car can adjust depending on the different parameters that and environments that the car is
exactly.
traveling on, right? And then why are you
Be-
why do we do this? Like what are the benefits? And then um,
because
basically what's wrong with the previous model?
there is nothing wrong with the previous model, but the previous model is standalone value of speed may not be optimal. But if you give the range of value, there are many multi-parametric optimization constraints that we can impose into the vehicle. As an example, I'm not just talking of fuel economy. If you want a better fuel economy, then go at only 55 miles per hour, which is the best green zone for the car. That's not necessary
Mm.
to. We need to optimize the trip based on the dynamic state of the car, because car interacts with mainly two elements in real time. One element is driver, the other element is environment. Environment includes even external air temperature, the wind velocity, the terrain, the friction, uh, the curvature, and many aspects. So we consider all these factors and try to correlate the dynamic state of the vehicle with the performance parameters.
Yep.
So based on that, we change the speed in such a way that trip is optimized and as well as the performance is also optimized. Although I'm not getting into complete details of optimization criteria, but yes, it is one of the main goals of that. So we did some kind of simulations on this, and at the end of the day, we maintain the trip time to be optimal, and as well as lot of saving of fuel, and as well as the performance overall performance parameter as such. The instantaneous engine efficiency has been increased a lot.
I see. Yeah. So, for example, like if a car, let's say, for example, is like having is climbing a hill, or like is on a very wet terrain, or like it's very hot outside, I'm sure the
Mm.
car needs to make some adjustments to the speed of the vehicle, right? And that's
Exactly.
basically how you optimize this depending on the
Yeah,
environment, right?
exactly. Based on the three questions that you have answered, first thing, if it is going up the hill, and if I set a value of like 65 to 75 as an example, not uphill is
Yep.
not more than 30 degrees inclination or something like that. Maybe on a regular terrain profile, you do have upslopes and downslopes. So what would happen is it will go to the minimal value of 65 as an example. When you're talking of the hot condition on the client, let us suppose you're driving in Arizona with high temperatures, external temperatures, then the optimization criteria would be engine surface temperature. Engine surface temperature should be around 90 degrees Fahrenheit, centigrade, I think 194 degrees Fahrenheit approximately. So based on the speed adjustments and the thrust and acceleration provided to the car will be changing. So that's how we had optimized the algorithm.
Yep. And I'm sure, like other than that, um, like there are a lot of moving parts inside of vehicle. So it means like if you're going 70 miles per hour, and under different terrains, different situations, the mechanical parts are also working like differently, even though they are constantly on 70 miles per hour, right? So I think by based on, like, correct me if I'm wrong, but by having the room for adjustment, the machine knows better like what's happening behind the moving vehicle, right? Inside the machine, the machine knows better, so it can like adjust the values
Exactly.
to optimize like the engine, so it doesn't like um, stop moving or like change the speed of the mechanical movement in the cards like very abruptly. Is that something like that? Is
Yeah,
that correct?
yeah. You asked a very good question. There are, to precisely speaking, there are around 3,000 components in an engine powertrain. But whereas in electric vehicle there are around only 300 components. So while moving with
Oh,
high
that's a big
momentums,
difference.
yeah, there's a big diff. That's the reason people world is converting to electric vehicle. One of the reasons is for that. There's a lot of change in the
Yep.
supply chain and everything. So in those moving parts, there's a lot of wear and tear. A lot of many things are happening inside the car. It's a complicated system altogether. But in our work, we first focused only on performance elements, which is of primary priority. The movement of parts, how the things are optimized, will come into the chapter of the vehicle health. Probably that could be a future work of our work, of our research. Probably.
By health, you
But
mean like the longevity of like
yeah,
different
exactly,
components inside? All right.
exactly. That's
That's
that's not been considered at all in our work, right? As of now, as of now.
but it's a
Mm.
possible like implementation later, right?
Yeah, that's one of the hot topics right now. I'm not talking of longevity of any component, the longevity of battery health, battery life, motor
Ah,
health, inverter health for electric vehicles is one of the biggest research element which is going on across the globe. So if we get into those things for and you apply for electric vehicles, definitely it's a very good, very big boon for the system altogether.
I see. Yep.
Mm.
And then what I see interesting is like it's sort of like you give more of the decision making to the car, but like it's still you're the person in control because you're giving the range, right? You're still inputting
Exactly.
that number. And
Yeah.
so my question is this some kind of like the next revolution for adaptive cruise control? And do you see this as like a bridge between the, let's say, the adaptive cruise control, lane keep assist that's already in the vehicle right now, and this is like the bridge between that into the full autonomy of vehicles? This is it something like that?
That's definitely a very good question, actually, because first thing is I would like to explain that there are certain federal laws imposed by the government onto the automotive systems. What you mentioned
Yep.
is correct. So there are certain features which are functioning on its own. As an example, the crankshaft timing, spark ignition timing. The driver is not commanding that, right? It is taken care of by the engineers and the control algorithms inside the car. The second thing is the driver just activates it. He doesn't do anything beyond that. Third thing is they activate it and as well as put some values to that. As an example, cabin temperature. You activate the HVAC system and also you set a value of say 70 degrees Fahrenheit in your car. So those are the kind of freedom the driver is given, and the car has to follow the driver's command. It's a prerogative of the driver.
Yep.
So in this scenario, we are putting a range of values. It means we are still following the prerogative drivers. We are obliging all the federal laws. That is one point. Second thing, yes, what you said is correct. In the fully autonomous, in the semi-autonomous or fully autonomous car, this is one of the deployed features. The latest example that I can give you is Super Cruise of General Motors vehicles. We had been actively collaborating with them. In fact, we had a recent discussion with him and received an appreciation to our idea. This was not communicated before. Super Cruise is a feature in General Motors vehicles where once the driver activates it, it steers on its own and also maintains the set speed of the car given by the driver, basically. So here we are proposing a new functionality to the whole Super Cruise feature of General Motors vehicles. It is deployed everywhere across the globe. So yeah, we are turning towards semi-autonomous and fully autonomous based on this. And if you talk of autonomous, more than 90 to 95% part of work is being done to actually safely traverse vehicle. That is perception, path planning, localization, and all this. This is one of the biggest topics right now going on. So we had added on an additional element or a burden to the autonomous guys. It's not just safe traverse to the vehicle and also care about the automotive performance also.
Yep. So
So
it's
it's like
basically one
additional
of the
element.
components, one of the problems
Yeah.
of autonomous vehicle, and then like you're like tackling one subset of that, right?
Very small,
Yeah,
I can
in
say
a
a small
sense.
subset of it, yes, definitely, because autonomous itself is a big challenge. It has a huge
Yes.
ocean actually.
Yep.
So but because our lab doesn't focus on those elements of path planning or perception or anything like that, but I thought we will just focus on what we can do, so why not performance.
Yep. Yep.
Yeah.
And now I wanna let's talk about how do you conduct your research. Let's go back a little bit and
Mhm.
like let's talk about how do you do this? Like how do you collect your data, and then what type of cars are you using, and then maybe how many hours of data are you collecting, and then is there any stories of challenges you had while doing this research?
Definitely, there are very challenges
Yep.
because the thing is, the kind of theoretical model that we propose may not be accepted at across the globe. So we had to take certain permissions, and we received an acceptance from General Motors to use their car functionalities. So we have the entire Cadillac segment to which we received permission to test around. So what I did is I just drove the car randomly across in Michigan area because I'm from Michigan. So we had tested like
I can see
Cadillac.
the jacket also shows
Yeah,
Michigan, right?
so this is.
Yep. Yep.
I'm really happy being here. It's a wonderful place, Umesh. So we drove the car in different terrains, different paths. All the four models like CT5, CT4, XT6, Escalade, all the cars we have driven, activating cruise
How many
and
cars?
see
How many cars did you
like
test?
around five cars: XT6, CT5, CT4, Cadillac Escalade, Cadillac all-wheel drive. All are
Mm.
Cadillac segments. All five
Yep.
cars.
There are like big SUVs.
Yeah, a couple of them are big uses. CT5 and CT4 are sedans.
Oh, yep, yep, yep.
Yeah. So when we what we did is by activating the cruise in the car, we drove across the different terrains, and we collected the data. As an example, we collected the data using the regular tools which are being deployed, like NeoV and the car CAN signal that we extract from the car. They are pretty much the regular standard procedures. We haven't deviated from that. So once we get the CAN signal data, what we did is we analyzed different segments. As an example, uh, I activated 70 crews and traversed a segment of the path, like for example 10 minutes. And in that 10 minutes, the constant 70 is maintained, right? And using the infotainment maps, we get all the information regarding the environment, external air temperature, humidity, and terrain properties, what is the slope and everything. So what we observed is like instead of maintaining 70, can we deploy a speed profile? Like, let me give a simplest example. Like just an example. Okay, first 1 second or some 30 seconds you are in 70. After that you are at 71. And after that you are at 72. Then you come to 71. So we generated this speed profile based on the defined optimization criteria and repropose that criteria. And we
Yep.
forcefully induced that into the predictive model and saw the difference of automotive performance between the constant speed and predicted profile.
Mm,
And definitely there is a change in automotive performance parameters. So as of now, we had deployed everything computationally. This
mm,
is all computationally. So when you talk of challenge, the challenge will be deploying that in real-time vehicle. That itself is the biggest challenge. How do we
yep,
deploy our code and make that run in real time based on the speed profile?
yep.
So
And that
probably that's my
actually,
part of the future
yep.
work.
And that actually leads me to the next question. And I'm pretty sure like you get asked this a lot of times. Like,
Mhm.
do you have like an estimation that
Mhm.
something like this, your research, can be seen in actual cars in the streets? Like, in what's the time frame for that? And what will be the biggest challenge outside of the research itself, like regulations or like getting companies to believe in the research, or like what are the biggest challenges?
The I, the biggest challenge itself is the process which we need to be followed, because in automotive industry, even if you want to put a small hole in a small nut, it's a huge process to follow. It's a very big process to follow. Trust me, I had affiliated with
I
OEMs
mean,
in the
it
past.
involves people's life, so
Yeah,
it
exactly,
makes sense,
exactly.
right? Yeah,
Exactly.
right.
So as of now, we developed the computational model. We published some articles on this one, and we received appreciation from many people, including you. And recently, I'm in constant communication with General Motors actually, because they are one of
Yep.
our sponsors. So when I spoke with them, and they really liked this idea to deploy in the future, I also spoke with Haley, one of the technical specialists, and the other technical specialist, Curtis. There are two people with whom I'm in constant interaction with. And to deploy this, yes, it's a process to follow. Whatever process the OEM follows, they have to do it.
Yep.
So, but at least they are interested a lot. They are very much excited. That I can tell you.
Yep.
And if everything runs smoothly, probably in 25 or 26 model year, it's going to be there on roads.
Mm.
As of now, the companies are focusing on 24 model year. So I'm deploying that with like 1 or 2 year a gap of like 25 or 26.
Mm, okay. Yep. Yep. Yeah. I
Mhm.
mean that makes sense, but I believe some people might be like, oh, the research is done. It could be in the car. Like, let's see the car. Let's see it implemented next year. I mean, no,
No,
obviously,
no.
like, obviously, no.
Never a
Like some
possibility.
people just they just don't understand the
Yeah,
complexity, not just in the
that's how
research itself.
that's how the media
Yep.
projects. We worked on
Yep.
this year, we are launching next year. No, that doesn't work out that way. It is a
Yep.
very
Yep.
big process to
Yeah,
follow.
especially with hardware, like there are different
Exactly. We have
technical
software
stuff
teams.
behind
We
that,
have, yeah,
and also a lot involve a lot of people in the process, right?
approximately 14 departments are involved to make a small change in the feature. Approximately.
Mm, yep, yep, yep. Yep. And
Mhm.
okay, I have one final question.
Mhm.
Um, what's next for this research, or for you? Like, are you working on another research, or like, what are you looking for now?
We have forecasted many projects for the future actually, but I can tell you some of them as of
Yep.
now. As I
Yeah,
said,
give us a
my
little sneak
complete
peek. Yep.
yeah my work is completely focused on driver behavior vector, right? So one driver behavior vector is speed. The other thing would be cabin air temperature. That is one of the things which I'm focusing on. So how much cabin temperature that you want to put in? Why can't you put a range? Suppose if you are comfortable with your AC or condition between 67 to 73 Fahrenheit, put a range. And how the HVAC parameters or HVAC functionality could be ameliorated, basically
Yep.
enhance it. So then we would be focusing our complete attention on developing a brand new drive mode in the car, which increases automotive performance. That is our next task. And obviously, this is going to take a little bit of time in controls, deployment, launch, validation. It's a big process to follow, but parallelly, we're going to work on electric vehicles as well.
Yep.
The biggest challenge is like electric vehicles, the optimization criteria. It's not that straightforward that we think of. It is little more advanced technological inputs are required for that, for the battery, inverter, and motor. Because in that you just have engine, we have an engine output, but here we have many conglomeration of
Yep.
many things actually.
So basically, the parameters of like an internal combustion engines, like doing the research on internal combustion engine vehicles and also electric vehicles can be like very different, even though they
Very
are
very
both
different.
cars. Yeah, very different.
Exactly. Because I
That's
just can't say lower fuel economy is engines one of the parameters, but I can't say low charge or high charge.
yep,
That's
yep,
that. It's not that straightforward actually.
yep. And what about with your current research? Like, I mean, the adaptive cruise control research. Like, are you reaching out to car manufacturers, or are you like what's next in the step? Like, you have your paper, and
Yeah.
then like, what's the next step?
Yeah, me and my lab actually, we are trying to contact certain OEMs. As I said, we just start with General Motors actually, but
Oh, yeah.
once we receive that acceptance from them, we would like to really work on it because, as I said, it's a huge process to follow. But we definitely received a lot of appreciation from them.
Yep, yep. All right, Srikant, I think that's. I mean, thank you very much for coming. I'm pretty sure a lot of our viewers here are going to be inspired and they'll learn something out of this chat. And
Absolutely.
yeah, thank you very much for coming.
Yeah, definitely. I'm really excited, and thank you, Wevolver. Thank you to you. Thank you to Joe. I had been coordinating with you all, and thanks for the appreciation. And I would like to thank my mentor also, Dr. Malik, for supporting all these activities and research. He had been a great support for this. Otherwise, it would have not happened because it was my idea. I was like thinking more theoretically as a young researcher, but he's more experienced. We want to put it properly, so he's shaped up a lot.